ignore.
Okay. So I want to just briefly review the sort of outline here. Graph theory basics. What is graph theory? Why do we care? The world is a graph. Visual adjacencies versus conceptual adjacencies. Gestalt theory. I threw in skeuomorphisms versus affordances. That's a kind of sidebar question, sidebar thing. And then just usable dimensionality. I'm hoping to refine this video, so if anyone later is watching it and I haven't gotten around to doing that yet, I'm sorry, but we'll do the best we can. So first of all, Alex, what's your level of understanding of the super basics of graph theory? Do you have any sort of base understanding? And it's totally okay if not.
Yeah, let's assume that I don't.
Okay, so what exactly is a graph? We're not talking about the pie chart kind of graph. We're talking about the mathematical concept. And there's some great YouTube videos that I might recommend that will help build upon this. But fundamentally, a graph is an abstract mathematical structure that describes entities and relationships between those entities. And so that could be any kind of entity and any kind of relationship. This is the most abstract thing that you can possibly imagine. So so in this case, we have a series of little drawings, and each of these drawings has dots and lines. The dots represent vertices or nodes. The lines represent edges or relationships. Those are vertex is synonymous with node, is synonymous with entity, was synonymous with thingy. Edge is some sort of connection or interface between two things. So in some of these diagrams, these are taken from a discussion that we'd had some time ago, where we had reviewed, and I apologize, I probably should have circulated the graph theory review video. But the idea is that the meaning of the graph has nothing to do with how you're drawing it, and everything to do with the abstract relationships. So if you rotate one of these, if you move the dots around on the page, as long as you maintain whatever relationships are there, if you move the node but the line the line adjusts to continue connecting the nodes, that would represent the abstract relationship. So Alice is married to Bob, and it doesn't matter if you talk about Bob first or second, they have a relationship that doesn't change when Alice takes an airplane flight or whatever. So so that's that's a sort of really basic concept. So this prompt says how many graphs are on this page, and it's a trick question because we haven't defined how many graphs are on this page. It could be one graph where we have 3 clusters of nodes that are not connected, or it could be 3 different graphs. Either way, we have a series of vertices and edges between some of those vertices that create the visual that we are visualizing in this way here. So are there any questions before I go too much deeper into the graph theory basics? Like any questions about what I've talked about so far?
Nope, so far so good.
Okay. In our previous discussions, we talked about connected graphs versus not connected graphs. So I'll put you on the spot, Alex. What are the differences between this graph and the one on the left? If we assume that that the little partition means that yes, they are 2 separate graphs.
I don't see much difference there.
Yeah, exactly. They're the same. We're drawing them differently, but how we draw the graph does not have any bearing on the graph itself. Mm-hmm. So in this case, we're we're documenting the rules of the game rock, paper, scissors. And then I believe, I forget why there's a third one, but by cuts, I think that may be redundant. But do we have, yeah, I think this is talking about edge weights, which is, I don't think we need to get into, but you could think of it as the ability to attach a property to each of these edges. So scissors, cut, paper, cuts is the weight, is the property of that edge. Paper covers rock. Rock smashes scissors. Does that make sense?
Yeah, it does.
Okay. And I think we probably did this again. Oh yeah, yeah. This is just the sort of continuation of that. Let's see. Okay, so in this case, we were diagramming the outline, the EDVO outline. How does it work if I create a bulleted list with 3 bullets? And this is just documenting that actually the bulleted list in EDVO is a subgraph. So if I create a bulleted list here, and I say this suggests my questions, I think that that this represents what we're talking about in the diagram. That this suggests is one vertex with a discrete identity. My questions is a different vertex. This is not just a big blob of markdown somewhere. Each of these things are vertices in the graph, and there's an edge. Let's say I forget what. Oh, I think we had called it building minimum. I'll just reproduce that. So, so in this case, we have one vertex for the member itself, one vertex for this suggests, one vertex for my questions, one vertex for I think, and there's 3 edges here between each bullet point and the member card.
Mm-hmm.
So, and if I say, you know, A, B, C, then there's 3 edges between. There's one edge between A and this suggests, one edge between B, one edge between C and this suggests. The actual value that I'm typing in here is a parameter on the vertex, but you can, yeah. Hopefully that makes sense. I can go into more detail if desired. Does that, any questions on that in terms of just the basic functioning of how, like the basic functioning of EDVO in terms of the kind of things that we consider vertices and edges, and how this, even though a bulleted list doesn't look like how we, you know, how you might typically draw the abstract graph, that it is nonetheless a graph, or more accurately, a subgraph of your broader graph. Does that make sense?
I'm a little bit lost on this ABC stuff. So we have a connection between building a minimum viable product and this suggests.
Yep.
So there are two nodes, and there is an edge between them, and then within this suggests we have a bulleted list, and all of the bullets in the list connected to this suggests. If we'll kind of like zoom into that node, is this correct understanding?
The rendering system, the code that renders this member card and child components is recursive. So it, what that means is that it, for anyone not familiar with recursion, it means that you have a function that can call another function that can call another function, and it will continue in a nested fashion to do that as needed. So I think one useful exercise to look at is count the number of vertices in this member card. just inside of the box for this member card. So count the vertices.
Yeah. So basically, like we can expand this suggest and like draw 3 additional vertices, and they are going to be connected to this suggest
with an edge.
Yeah, and then if we will have like sub bullets for A or sub bullets for B, it will go even deeper.
Exactly. So I would say counting these, it's one vertex for the card. This suggests A, B, C, my questions, and I think. So that's 7 vertices. And if we count the edges, that's let's not count the edge between the card and the topic space, although there is one. So there's one edge between this suggests and building a minimum viable product. One edge between my questions and building a minimum. One edge between I think and building a minimum. There's one edge between A and this suggests, B and this suggests, C and this suggests. 6 edges.
Yeah, though there are no edges between A and building the minimum viable product, right? Because those are encompassed within the edge between the suggest and.
Not in this particular case, but I think a key thing to understand about the data model is that we are trying to allow you to model anything. And of course, you need to have a way of performing data entry and of visualizing that in some fashion. But we can record more edges than we display. And one of those things is visit tracking. So in certain cases, when we visit, particularly a topic space, we will create edges. Actually, I don't know if that happens, if that scenario creates edges, but there are various cases where we will create additional edges that we might use in the future, or that we use in different ways. And so anytime I think the goal is to capture as much meaning as we can in the situation. So if there was some potential relationship between A and B, even if we didn't want to draw it in the outline, we might still consider capturing that, perhaps for a different mode of rendering, or perhaps for future use. And each of these edges has what we call a role. A role is basically just a sort of it's a type that allows us to differentiate. So in this particular case, I believe the outline utilizes a category of, or I forget the exact name of the edge, but it basically is saying like there's just one type of edge that we use for outlines, and there's a different type of edge that we use for implicit relations. So if I let me just make this a pretty color and go like that. So when I got the sticky note close enough to the outline card, we have some logic in there that says, okay, I'm within a certain number of pixels. Let's make an implicit relationship. This might be useful later because who knows? Like in the search process, we want to uncover serendipities, etc. And when I move it apart, it breaks the relationship. It archives that edge. So there's a bunch of different ways that we use edges, and it's like what kind of information do you want to record that relates two vertices together? Well, sky's the limit. So, and then one other thing I want to talk about is transclusion. So let's transclude A, and I'm doing this by holding the Alt key and dragging, and so I should be able to do this. And so so when I did that, and I realized there are visual concerns that we have to find some way to signify to the user, hey, this thing is visible in more than one place. Notwithstanding that UI UX question, the point is that I've done what we call a transclusion. This is not our term. This is Ted Nelson's term from back in the 70s and 80s. So what this means is that now if we count the vertices, the number of the vertices has not changed. We have not added a new vertex. We've added a new edge. And so now the rendering code, when it is rendering this subgraph, it sees the alpha vertex twice. And there are cases where that's useful. This is not necessarily the most useful case, but it's at least clear for demonstration purposes. The most useful case is that I have two totally separate contexts that refer to the same Alice Jones. And so when I include my Alice Jones card, I don't want to have two Alice Jones cards.
Right.
So this is fundamentally different than a containment kind of structure. And for that reason, we're very careful about using the word parent and child when we refer to the data model. Essentially, we don't. There are no parents and children in the data model. The graph has no parent-child relationships. The rendering does. The rendering of whatever the rendering logic decides. Hey, I have some starting point, which in this particular case is the topic space, a small theory interlude. That's our sort of seed, and that's what we use to create the root rendering node. We're not talking about rendering in too much detail here, but fundamentally the rendering code decides what relationships within the graph do I follow, and I'm going to create a render tree from those queries recursively. Does that make sense?
Not the last part.
Okay. So the root node. So let's just get a rough idea of what our rendering nodes are. So we start out with a topic space, and a space is just a way to view a topic, right? It's not a topic space is not really a first class thing. It's just a view. So we've got a topic ID, crucially, and that topic ID is the vertex ID, really. The topic is just a vertex with a name, by the way, in our nomenclature. So so that's the vertex ID for a small theory interlude vertex. A small theory interlude is just a property attached to that vertex, by the way, the name property. So the rendering code says, okay, great. I am a topic space. I do topic spacey kind of things, and the main thing that I do as a topic space is I have members, and I want to get those members, and I want to draw those members. So it's going to say, all right, let me find all of the member of edges that are inbound to me. We happen to index that in reverse, by the way. We call those backrefs, but it's basically just an index of edges. So when B points to A with an edge, A has a backref to B. So the rendering code says for the topic space says, hey, let me find all the backrefs of type member of. And okay, great. I'm going to go create a member view model node for each of those. And so the member says, oh, okay, what kind of member what's my display mode? Oh, okay, first it says, like, do I have a body? If it's a body like an image, then I display that. If I don't, then let me display my outline. And then it creates the outline component. And the outline component says, okay, I'm an outline component. Let me query the graph to see which vertices have a category edge or a category background, strictly speaking. And so it's the view model is recursively querying the graph to figure out what things do I want to display in this context. Does that make sense?
Yeah, I think so.
Okay, so that's it. that is the depth that I wanted to go into for graph theory. Are there any? There's a lot of like other little details to graph theory, but as long as you understand that the vertices exist abstractly, they don't have any sort of position innately. The edges exist abstractly. There's no one right configuration of these. You can rearrange any of these graphs visually, and they remain exactly the same graphs, just like this one. These are the same graph. If you assume the identities of each of the vertices are the same.
Right.
So, any other questions on graph theory basics?
No, I think so far so good.
Okay. So, what can we do with graph theory? So, so the world is a graph. Everything is a graph. I literally can use a graph to describe anything that you ask me to. And so I think the easiest one is U.S. states. If we just draw the subgraph, we don't have to do all 50 states here. If we focus on the subgraph of California, Oregon, Arizona, and Nevada. If you look at the map, there are literally edges on the map where Nevada touches Arizona. And Arizona touches California, and California touches Nevada, and California touches Oregon, and Oregon touches Nevada. I think I got all of those. 1, 2, 3, 4. Oh, I think I missed one. Which one did I miss? Nevada, Arizona, California. There we go. Okay. So, so if you look on the map, this is why they're called edges, because literally they are adjacencies. Nevada is touching California, and so we simplify. If you take the whole border between the two states, which is this funny shape here, right? But we're not trying to model the geography here. We're trying to model the relationship abstractly. Right. So we squish that whole border down to a point, essentially, and we say California has an edge with Nevada.
Right. It's like a true-false thingy, and if it's true, then there is a connection. If it's false, then there is none.
Pretty much, yeah. And so we can add additional information on top of that edge if we want to, and that's the whole like edge weights thing. But let's save that for another time. So fundamentally, I think you can use graphs to model geopolitical boundaries. You can
maybe real quick on the weights of the edges. So hypothetically, if Nevada and California has a longer border than California and Oregon, we can attach that to the edge and say, the weight of this edge is 3 and the weight of this edge is 1, and then if that's the question,
or it could even be complex, and you could say that this edge, weight is just a funny mathematical term. You can really think of it as a value or a parameter that you put on that, and so we could say it doesn't have to be a single value. It could be as many values as we want to attach. So we could say that the length of the border is such and such miles, and the authority for this border is the U.S. federal government, and so on and so forth. Like whatever we want to put on there, we can put on there.
Right. And then we can use the weights of the edges to find the nodes itself, right? Like to display them. Say like, this thing has like 25 billion connections. Display only ones which has the weight of 3 and more. But ignore the others.
And so fundamentally, this is the most simple way to record any kind of relationship data. So it is as general as it gets. Okay. So just some other examples of graphs. The girls playing Ring Around the Rosie. We can form a graph between the girls. These are the edges, and these are the nodes. We have, and there's a little bit of crossover here. There's a relationship between the state of these apples. So we can model the state of the decay of the apple as vertices and the relationships between them as a sort of time progression. We could say that the relationship between Chris Rock and Will Smith, you know, we can talk about the relationships between musical notes. That there's a lot of different ways that we can use graphs to model things in the physical world. And yeah, so I'm sure we could come up with lots of others, but I think this is a good representative sample.
Yeah, it is.
Okay. Any thoughts or questions on this aspect?
With apples, it's going to be a linear graph, right? The last one is not going to be connected to the first one, unless we treat the time as a non-linear thing.
Yeah, and a lot of it depends on how we want to model it. There, you know, there's variations, but
yeah, that makes sense.
Okay. So I think it's useful to talk about visual adjacencies versus conceptual adjacencies. And so what we have right here is a model of the caffeine molecule, which is a graph that the individual atoms in this molecule are modeled with a vertex for each atom and edges between the atoms. And so you could say, okay, this is a physical thing. Like I touch this model, it's made out of plastic. I can snap the little pieces apart, snap the carbons and the hydrogens apart. But this is also, so, you know, we're talking about like physical adjacencies. Like these are pieces of plastic that I can snap together and break apart. This is a physical graph. But it's also a conceptual graph, because this, despite the fact that it's modeling the caffeine molecule, is not a caffeine molecule. So we have some sort of distance between what a real caffeine molecule is, which is a physical graph, versus this model of a caffeine molecule, which is also a physical graph, but it's also a conceptual graph. So we are representing conceptually, we're representing visually, I should say, that which is conceptually abstract, and that there is some distance between these. So this is a fun example because it's a little bit of a brain twister, because it's both. It is a physical graph and a conceptual graph at the same time. So I think one other, I was struggling to find like a really accessible way to describe this in other terms, and I think telecommunications is probably the main way that we create tension in this day and age, that we create tension between physical graphs and conceptual graphs. That I am able to communicate with people who are across the globe very quickly. So the physical actors here are spatially disparate, but the conceptual or visual representation is physically quite proximate. I am, you know, in this Meet call, I see you right now, right next to Shireen, but you are on the opposite sides of the country. So my visual graph has the two of you very close together, but the physical graph has the two of you very far apart. And I think this concept of the tension between the way we record things versus, or the way, it's like the way things are, the way we record things and the way we visualize things, is both the superpower that we have. This is supremely useful that I'm able to talk to you and see both of you together on the same screen. But it also comes with limitations. And it's not just network latency, it's also, there's only so much space on my screen, because my screen is a two-dimensional plane. And my graph is potentially of unlimited size. So there's only so many pixels. There's only so much stuff that I can make sense of at one time on my screen. So we have to be selective. So I want to talk a little bit about, let's actually do this in reverse order. I want to talk about the crossing problem, mostly because this is a little game, super simple game, where they just give you a random graph that happens to be planar, and that you can do. See if I can not embarrass myself. Let's see. You rearrange the graph. It's all the same. It's all the same graph.
Also, the goal is to untangle it.
Yeah, it's the goal is to untangle it so that none of the lines cross each other.
Yeah.
Let's see. Okay, there we go. So I did it. So now none of the edges cross each other. I'm able to flatten this graph out onto a piece of paper, and nothing crosses. So this is a very special class of graph that is not, I mean, it's not uncommon, but you are definitely not guaranteed that all graphs can be drawn in this way.
Yep.
Most can't. Most will have some sort of crossing, and like, what does this mean? What this really means is that we have more dimensionality in the underlying model than we have in our display media.
I mean, assuming that we treat crossings as something bad.
Well, it's like, not bad. It's not bad. It's just I mean, it's just inevitable. And that, like, say for example, when I have this crossing, because there's a relatively small number of nodes in this graph, I can still understand it. I can visually follow those lines. It gets a little bit in the middle here. It gets a little bit confusing because I'm like, okay, I've got 2 lines crossing over 3 lines, and I have to kind of follow that. So it increases the cognitive load a little bit, but it's still manageable. So I think this example is fun because it demonstrates a couple things. It demonstrates that this graph is the same graph when I rearrange it. The visualization is not a function of the graph. That's a function of the visualization. So it also demonstrates that most graphs, maybe a little bit more subtly, it demonstrates that most graphs are non-planar, and we cannot display them on a 2-dimensional plane perfectly. Some are way worse than that. If we had a highly connected graph, if we had a highly connected graph, you would really struggle to be able to express that graph perfectly on a 2-dimensional screen. So so this is one way of looking at the visual adjacency versus conceptual adjacency. Conceptually, we are unlimited in terms of what we can model. We can connect any concept in the universe to any other concept in the universe. Physically,
yep,
there are some constraints. You're constrained by spatial dimensions. Excuse me. But when we record things that are distant, we're creating a conceptual model. And so we go back into, we go from this sort of limited, the spatial graphs are limited in the ways they can be connected. Conceptual graphs are unlimited in the ways they can be connected. And then fundamentally what we're working on, and the power of such a system is, this is a conceptual graph. You can connect anything you want to any other thing, but then we have to deal, on the other side, we have to deal with the fact that we have to visualize this somehow, and we've got to bring it back to the physical. So so that's a tension that we fight, and fundamentally and I think this is where the cartography example gets really fun, is we have to pick and choose. Excuse me.
Yeah, because cartography is not perfect, and we have different kinds of projections, and all of them skewed in some forms or fashions. And the same is going to happen to the graphs.
Exactly. So this map is not a geographical map. This is a map of chemistry terms and their relationships. And there's there's actually a cartography professor at a local university who works on this kind of stuff, and it's super cool as far as I'm concerned. But I think this demonstrates that a cartographer is just a specialty graph visualizer. And what they're doing is they're trying to anticipate the needs of the user, and they're trying to see, okay, are you using this map for a road trip? Are you using this to develop some sort of political understanding? Are you using this? And usually it's some blend. They're trying to predict what persona is consuming this map, and of the massive number of geopolitical and civil and cultural facts and whatever that I might put on here, how do I pare that back so that you can actually read the damn thing? So I think it's super interesting to see photography applied to things other than geographical graphs. But I think it's a really good demonstration of this tension. We cannot show every geopolitical, civil, cultural fact on a map. We can't do it in EDVO either. So we have to be selective. And the process by which we are selective of which exact slice of the subgraph are we rendering in which case, and how do we create all of the nuances that make this intuitive and powerful, like that's the art here.
Yeah.
Okay. Any other questions on that tension between visual and concept? It's really like physical, conceptual, visual. That's what I should have called this.
Yeah, so I do like how you describe it at first as well, like as a visual conceptual. I'm sorry, physical conceptual physical. Because when you deal with the screens and interfaces and a finite amount of pixels on the screen, it kind of like brings that physicality aspect back. So yeah, that's pretty cool.
Yeah. Okay. Any other questions on that? No. Okay. So a little touch on Gestalt, excuse me, Gestalt theory. And I realize this is a deep well here. I'm not trying to do Gestalt theory justice, but just trying to convey the general flavor of it. Without getting existential, the stuff that you're looking at on the screen is not the stuff you think it is. It's just dots, man. So, if you look in figure A, you see the triangle, right?
Yep.
But there's no triangle.
Right.
You can see whatever this sort of slightly snaky shape is between the two apostrophe style things. You can see the ball, the spiky ball, but there's no ball. You can see the snake on the the water snake in figure D, and so I think it's really important to think about, if briefly, to think about the things that we put on the screen are not really things. We're trying to key into some perceptual, some primal perceptual system, and symbolize something else. So
so it's immediately recognizable as something that you can interact with. It's kind of like taps into what you have here with a skeuomorphism. When like everybody try to draw a button as a physical button, therefore it invokes the idea that you can press on it and interact with it, and then at some point we stripe it down to the flat design because everybody was trained to recognize things in that fashion, and it's not a problem anymore.
Exactly. And so some of this is nature and some of this is nurture, that humans ship hardwired with some of these like pattern. If you really want to think about Gestalt theory, it's about pattern matching. That humans are big pattern matching machines, and some of these patterns that we match are hard coded from birth. Some of them are cultural, and some of them are learned, and frankly, that's how the culture advances. But but in any case, that we're always, it's all pattern matching. If I have a scrambled letters on the screen, if you're going to try to pattern match over that, and if you're not able to immediately discern any words, then you're going to match it as scattered letters. But then you start to just tweak the position of the letters just enough, and you're like, oh, I see words. Okay, got it. And so it flips from being one thing to the other. And I should have included the famous like profile of people versus the vase. But as it flips in your perception to whichever one is stronger. And some of those fun illusions, play with your visual system because it's like 50% vase and 50% two people facing each other. But this is the fundamental nature of pattern matching and gestalts. So that's something that we have to think about when we're building UI affordances. Is it's not just, oh, this is a thing on the screen. It's what is it next to, and what are we symbolizing with those things being next to each other, and are we accidentally signaling things we don't want to signal, or are we intentionally signaling something? And it's surprisingly powerful just by like adding a drop shadow, changing the color, putting a thing next to each other, having one thing appear temporally after another thing. There's all kinds of little changes that can trigger these pattern matching behaviors and symbolize something. And so doing that well is fundamentally part of our challenge. So so that's a good segue into skeuomorphisms. And I don't know if I use the industry accepted definition of skeuomorphism, but the way I look at it is a skeuomorphism is an affordance that you already understand. That's maybe that's a funny way to put it. We might want to unpack that a little bit, but I would argue that the original like iOS 1.0 notepad with the college rule paper is like, that's the canonical industry example of a skeuomorphism. But also a doorknob is a skeuomorphism. You don't ask, how do I use that thing? You just know, because it's ingrained into you culturally. There doesn't have to be a placard above it that says, to open door, turn knob. It's like, I know. It's automatic.
Yeah.
Right?
Yeah. I think doorknob will fall into that example if you use like a digital doorknob to imitate, I don't know, like a login or something, right? That draws that connection between a thing which is not a thing, that representation of the thing, and something in the real world that you used to use and know how to use.
And so I'm not super married to this definition, but in terms of the way I think about it is like, it's not just using the doorknob on the login page. Like I think that's a pretty obnoxious version of a skeuomorphism. But I would argue that the doorknob itself is skeuomorphic because it's not the same knob that you grew up with. When you grew up in your house, you turned doorknobs to get around the house. And when I invite you over to dinner to my house, you know how to use the doorknob. I don't have to. It's not a whole new learning experience because it's a familiar shape and size and position, and it looks like it operates that way, and you just pattern match it as a doorknob. So I'm not gonna. This is not a hill I'm gonna die on in terms of like convincing industry that physical things are skeuomorphisms, but I think it's a useful way of thinking about it. And
it's interesting.
And I was a little pressed for time, but searching for like examples of affordances that are a little bit less skeuomorphic, and I think the hamburger menu is an interesting example of something that maybe like started out as a skeuomorphism and kind of stopped being, but like, what the heck does a hamburger menu mean? But yet everyone knows what it is. And it's a little interesting thing that's different than the rest of the UI on the page. And you're like, what is that thing? Oh, it does a thing. Oh, that expands this. Got it. Okay. And so you could argue that this is either semi-skeuomorphic or non-skeuomorphic. And yet, it's an affordance. It's something that people can use and can get comfortable with. And so, at this point, pretty much anybody who's ever used a computer knows what a hamburger menu is. They might not know that that's what it's called, but they know what it is, and they have a general understanding that this is going to reveal some sort of configuration or extra or more or whatever.
Mm-hmm.
So I think it's important to bear in mind as we go through our design process, and this is not me speaking to you, Alex. I'm sure you know this, but this is just kind of the way I think. That some of these affordances, and I would say the doorknob is an affordance, the notepad is an affordance, the original actual physical college rule paper is an affordance, that some of these affordances are more skeuomorphic, i.e. the user has an innate understanding and pattern matching for them and for the gestalts that comprise them. Some of them less so, and the user will require some training. And so I think it's pretty clear in the UX community that that hard skeuomorphism or forced skeuomorphism, like the college rule paper and the note app, is passé, and you definitely don't want to do that for everything. You know, I don't know if that's the reason Microsoft Bob failed, but it definitely was part. You know, it didn't help. So so there are inevitably going to be ways in which we have to train users on what our affordances are, and as I see it, it's about a path where we initially give them some training wheels, but at some point they're going to have to learn how to ride the bike. Okay.
Yeah, 100%.
Yeah. Any other? Yeah. Go ahead.
Yeah, I was looking yesterday at Mira versus FigJam, and it was interesting how FigJam is still using a lot of skeuomorphic patterns. Like if you like look at the toolbar, I will steal a screen share just for a second.
Okay.
Just to show you what I'm talking about. I think it's like a very powerful thing that they choose to do. So like they want to build a collaborative whiteboard experience for everyone, right? And they have like a bunch of tools. They have like markers, stickies. They have those little how do you call them? Oh my god.
Emojis?
Almost like the other word for emojis.
Avatars?
Maybe like the ones that you use in the messengers, like in Telegram.
Yeah.
So they have that stuff.
And emojis.
Yeah. So and they like really use like a lot of like physical representations. For example, when you select a marker, you can see like the one which is hard one, the one which is like a little bit more flattened. They're literally using a tape and eraser. And one may argue that right now it's not necessarily like important to use the physical resemblances of the objects to depict those tools. But at the same time, it's kind of like immediately clear what they do, how they are going to behave, and I think it's creating like more connection to the physical whiteboard than Mira does, and it's also kind of like just visually interesting. It's cool, it's fun to use, and you getting an idea of what the object is going to do even before you're selecting and using that. So that's a good example of using skeuomorphism in the interfaces right now. And on the counterpart, we have Mira with their toolbox. Let's see, where is one? Oh yeah, it's just here on the side, right? It's like our classical approach to the toolbox, resembles Photoshop to some extent, but for example, this marker is much less inviting marker than the previous one, and I cannot tell how the color is going to work, whether it's going to be a flat tip or a rounded tip, etc. And this is okay. People are getting trained to use this, and maybe like for the power users, it's actually a more effective interface. But for the entry users, people who are just getting more familiar with the tool, or for people who can appreciate, like those little visual details, I think FigJam is going to work much better. But at the same time, it's the same thing, and the functionality is pretty much the same there.
So I want to add a little like Edvo related kind of decision we made about the toolbar versus something else. And by the way, there's a huge opportunity in improving the execution of it and the design of it. But I just want to go back to Daniel's screen. You know, you'll see the radial bar. Daniel, if you can just expand it. The intention here, I felt like, so before we used to have a Mira-like toolbar on the left, and every single person that would come in would say, well, this is a whiteboard. Not that that's necessarily changed, but I'm noticing it's definitely decreased. That's not the first thing that they say. But I didn't want people to perceive their spaces as just this like 2D whiteboard that, you know, you either have stuff on it or you remove stuff, but there's no real depth to it. There's no real dimensionality to it. And so what we were thinking is really this is a 3D or really an n degree like n dimension environment, and I wanted to pull the radial bar from video games and how you actually navigate rich information environments, and you go deep into something or you come back out and do a bird's eye, but it's like that steering stick in a way. And so it's like these are the types of, like, this is why we're thinking about this, as if we just see this as this like 2D blank page, you're gonna make vastly different choices around the way tooling is presented and how someone navigates it. Whereas like when we've been designing the interface, we're pulling more from like video game design elements. Again, plenty to discuss here, plenty to optimize here, but I wanted to call that out on this topic.
Yeah, that's a great call out. And I think it's worth noting that we've had some discussions about how to have spaces become. Imagine that the space is not a flat pane of glass, but rather a deformable rubber sheet where you can stretch and squish stuff, and where I might have things between these two cards where I zoom in, and the two cards on the side stop getting larger, but the thing in the middle gets bigger. And you imagine that this is a rubber sheet where I'm not zooming in on the whole sheet, I'm stretching this part. So there's pros and cons to that, and that's a whole other conversation, but I just wanted to convey that that we're not locked into a canvas style format, that we're trying to, the goal is not to make a canvas with things on it. The goal is to visualize conceptual adjacencies in the most intuitive way possible, bearing in mind that it's not just about one snapshot, I'm here, hey look, all my conceptual adjacencies done. It's like, no, actually this is a fly through or a flow where we're moving and shifting and changing and rotating, and that there may be things that are related to what's on my space here that I want to transition to where it's a slightly different view. And so what are the ways I can do that are non-jarring, that offer continuity of experience, that allow me to, you know, fundamentally it's there are more relationships in the graph than we can visualize in a way that the user will understand. So how do we slice it, and how does that slice move through the highly dimensional graph, bearing in mind that we still have to put this on a two-dimensional screen.
Yeah. And I want to call out one more thing. Dar, are portals demoable in staging?
To an extent. There's some issues that Rashida's still working on, but you can still see the general concept of it.
Daniel, do you want to take a stab at maybe demoing a portal in staging?
Actually, possibly, but I don't want to break my my space here. Dar, sure. Are you?
I'll do it. I'll do it.
Yeah, when I looked at your space, staging has rendering issues right now, so this space particularly, Daniel, gets really blinky.
Okay, got it.
Let me show you real quick. And hopefully I won't break anything, but we will try our best.
If it breaks, you just remove the portal.
Yeah. So this is my lovely Alex space. So I'm going to just go ahead and change this appearance to portal. And notice, Alex, now I have essentially gone into another space that I can zoom in and out of. I can pull things out. I can bring things in. And this is actually, until we broke it, my most valuable feature in Edvo. Well, I shouldn't say that. It's probably one of my top 3 most valuable features in Edvo. And it's because it allows for that like continuity without, like, I can just, you know, zoom into this like different dimension, right? I can zoom into this different universe that's still connected to kind of this like parent topic space that I'm in. And I can just like, I will zoom in here, and we've again talked about how, you know, you don't have to have like double zooms. But this is just another call out of when we unlocked portals is actually the first time I started seeing this, and this became very clear in also demos. I did it with external people where people like, oh, holy shit, this is like this is what really made the graph shine. Like people who didn't really understand graphs, they didn't say those words, but they were like, oh my God, this is like, I can go as deep into my brain as what people say, and then I can come back out and still have the surrounding context, and I can just follow these relationships, and that's really cool. So I wanted to show you this, and hope.
Yeah, this is super helpful, because I was wondering what the hell portals are.
Yeah.
And now it's clear. Thank you.
And the devil is decidedly in the details in terms of making it less fiddly and more intuitive. That's one of the things that we're working on with auto zoom, auto pan, because generally speaking, I don't want to ever be viewing a page where the main feature thing is 10% off the screen.
Yeah.
And you know, there's a lot of situations like that where we can do something smarter and it'll feel a lot less fiddly and just smooth and magical. So there's a lot of potential there.
Yeah, exactly. The interaction design is gonna be a very big topic. Like, if we want to have like a bunch of websites on the canvas and interact them in the same way we interact with the websites in the browser, like even common scroll or zoom becomes a challenge, because you have double scrolls, double zooms.
Yeah, which am I zooming? Which? Yeah.
Exactly.
Absolutely.
And I run in a situation, you know, yesterday I was playing with Edvo and I zoomed into the website and I make it like as big, you know, as the entire canvas, right? And now I cannot move canvas in any form or fashion. I stuck on the website, right? So that's kind of like an edge case. Maybe somebody would run it, maybe somebody would not, but it kind of like, you know, takes this problem of, you know, double interactions to the extreme.
In theory, you should be able to hit escape, but and then pan, but that's not obvious, and we need to expose that better. And there's a lot of, you know, there's a lot of things that, you know, a drop shadow or a glowing border or whatever can carry a surprising amount of weight in certain circumstances. Where like, am I inside or am I outside? That kind of context conveyance. So there's more to be done there in terms of the design work. Absolutely.
Yep.
Okay. So I just wanted to kind of close this out by talking about like, it's what are the dimensions that we can use? What are the you know, talking about physical, conceptual, physical. What, you know, this also does kind of apply to our on-ramps, because going from physical to conceptual, there's the you know, it's like anything you can do in the physical world, how do we adapt that to the conceptual? And there's lots of different ways that you can do that. Given the fact that we're mostly working on desktop computers and probably a little bit mobile, you know, what are the input modalities that we have? So let's set that whole like input conversation aside for a minute. But so this is the output. This is when we are translating back from conceptual to visual or actually physical. It's, you know, we've got the spatial dimensions of your screen. We have the temporal dimension. So I show you an A and then I show you B. And then we've got auditory. Unfortunately, we don't have olfactory or proprioceptive, but maybe someday. So it's just useful to remind ourselves, particularly of the temporal. I think the temporal is the most underappreciated dimension of display, in my view. That if I show you, you know, I show you thing A and I show you thing B, there's an either an implicit or relationship or an actual, you know, we're either intending to convey a relationship or we're not intending to convey a relationship. Either way, a relationship is conveyed. And the question is whether that rises above the noise floor, whether that is pattern matched by them, whether they see that, oh, thing A and then thing B, this is like hits my Gestalt recognizer, and I see that A and B is visualizing some relationship.
Yeah. Do you have an example of that you like?
A flip card, right? I show you one side of the card, and the animation helps kind of smooth things out, but strictly speaking, it's not required. That if it looks like a flip card and I show you thing A and then I show you thing B, if there's any, like just the fact that it was showing A and now it's showing B, if there's like a whole stream of them, like A, B, C, D, E, F, G, whatever, then there is no, then the pattern match for the sequence is stronger than the pattern match for the flip card relationship between A and B.
Yep.
So there are other kinds of ways that we can use the temporal dimension to demonstrate relationships, and I think it's just useful to think about. There's some residual that can be used in certain cases to demonstrate these things. We don't have to, like, we're gonna have to shove a lot onto the two-dimensional screen, but it doesn't have to all be there at once necessarily in order to convey these relationships effectively. And as long as we're not too annoying, we could potentially do auditory stuff. That matters a lot more in mobile, I think, and a lot less in desktop, just because of what people are accustomed to.
Yeah, and auditory stuff has a whole bunch of accessibility issues. Like you still need to pair it with the visual clues to make it useful.
Yep.
Plus, in the work environment, a lot of people working with muted sounds. So whatever audio design we decide to do, it may go to waste in many cases.
And I don't imagine that audio design will be high on our list anytime soon. But I think it's useful to go through the exercise, because it can be really easy for a lot of folks to get stuck in the whole, like, oh, I'm just drawing boxes kind of thing, and like this box is whatever. But I think in summary, I hope that this presentation conveys a little bit of understanding about how we think about graph data, why we think. I didn't actually cover why we think it's valuable. Think of it, but that might be an interesting conversation for another time.
Yeah. What I would love to do at some point, maybe as a part of jam sessions, is to try taking some of the concepts that you described today and try to lay them on some use cases that people might have while using it, right? And see how, like, what are those complexities, what are those dimensionalities are actually going to be useful in the context of their experience. I think, again, I'm just starting to wrap my head around it, right? You've been thinking about it for quite a long time, and maybe collectively we just jump in, take whatever use case it is, like planning a travel with friends, right? And then see what are those useful concepts out of the entirety of the graph theory and Gestalt theory and other things that we discussed today that can be sprinkled across that experience to make it useful, unique, cool, etc.
So there's and I think that's super cool. I look forward to that. I think there's one seed that might be worthy to plant on the topic of why a graph. And I think that this is actually really fundamental. And if you think about it, I'm trying to figure out the best way to frame it. We are creative individuals and very thoughtful individuals, but there are so many more things that people in the world could think or want to describe, or workflows that they might want to create, or whatever. There's so much possibility. There's so many combinations of things that I might cook in my kitchen,
Right.
and they're literally or metaphorically. And so, who are we to tell them what not to connect? No, you can connect these kinds of things, but not these kinds of things, because that's crazy, except for when it's not crazy. And
right.
So I think it's about removing as many constraints as we can to the relationships that people can form, because that's where creativity lives. That's where knowledge lives. That's where meaning and wisdom live, is in the connection of two things that were previously not connectable. Yeah. And I think this has, you can look at this as a sort of metaphor for all innovation, but also why, what are the roadblocks that we put up to the faithful representation of that? And some of those are in service to, business needs and are necessary, but some of those are unnecessary. And how do we remove as many of the unnecessary ones as possible?
Yeah, no, that makes complete sense. The only thing I want to bring there, you use this culinary metaphor, right? And what I believe we need to do is to produce cookbooks for people, because if you give them a bunch of ingredients and they can do anything they like with them, some people would go creative and try experimenting and maybe make something uneatable, but they still will have a good experience. But a lot of people need that cookbook, which will have 10 best recipes for the things which actually work. And those 10 recipes is probably going to become our 10 core use cases, or maybe 5 of them, or maybe even 3, whatever is the number.
Yeah. This is a great metaphor, and I like it. And I think the key mistake that I think a lot of people make in software, and for understandable reasons, is that they mistake the need for the cookbook, which I think is very real, for they create rails so that you can only make the things in the cookbook, and that is, I think, what we're trying to avoid.
Yeah, it's a big difference between core tools and tools which serving only one use case. For example, with Figma, it perceives as a interface design tool, right? But I literally did a flat planning, in the tool, just to figure out where to put couch and whether or not couch and the table would fit into the room, the way I like them to fit. And then years after I did that, I saw people starting to release a set of stencils for other people to do the room planning in Figma, and it actually becomes a pretty valid use case, because you can collaborate, you can bring in stuff, you can bring photos, you can match photos to the floor plans, and it's super fast and easy, and a lot of fun, because you can collaborate with your spouse or partner or I don't know, kids, on that. So there is going to be wild use cases which are not intended at the beginning, which is going to be popular at the tool, and it's super cool, and enabling giving people set of core tools to actually fuel their creativity is very important.
And final thought on that is, a lot of systems, for a variety of reasons, technical and cultural, use hierarchies or containment relationships to represent that kind of thing. When you open up a Google Doc, they don't let you include a paragraph from another Google Doc in it. Yeah, you can copy paste it, but it's a different paragraph now that just happens to start with the same content. And so a Google Doc is a container for words. It is not a graph of words. and similarly, you know, I think that's a sort of key differentiator, and why portals as one example of a way to pierce the container metaphor that that we can share in every which way, and that is a sort of fundamental superpower that we have.
Yeah, and I want to say, like, Notion, I think, went one step forward, and it started allowing for that paragraph to be, you know, essentially creating a graph of text. And I'm not quite sure how their interconnectivity with now their other components like tables and embeds actually work. But I think what we're trying to do is now go one step further, or maybe two steps further, which is it's really your graph of your knowledge. And I explain this to people. I'm like, look, you know, there's two elements of this. It's Notion is if you see it as a graph of text primarily, then Edvo is that graph of knowledge, more inclusive of the different types of knowledge you work with. And then whereas Figma is your way to interact intimately with your designs, and it's specifically for a design use case, Edvo is to interact intimately with your knowledge. And so it's like, I wish if I could within, you know, well, actually there's so anyways, those are kind of like the two pieces that I call out for people to help them understand, like, kind of our underlying approach.
I think it's fair to say we should probably, as we add more features to round out user demand, we should probably be taking a really hard look at a lot of the stuff that Notion does. But one thing that Notion does that we don't want to do is constrain users to a purely linear format, where this paragraph must, you know, it's like paragraph A, B, C, D, and that's all you get. That the canvas approach is it's one more dimension, and we don't want it to be a grid. So Canvas.
Yeah, 100%. I think infinite canvas is like one of the best inventions in the interfaces as of late.
Yeah, and it comes down to like the interaction of it, right? Like that is just more interactive. It feels more intimate. There's more of that connection, and I feel like that's what it produces. Side note, and we don't need to go down this route right now, but I wanted to call this out for all of us here. Brandon Boswell, which Daniel and Darlene have more context on than you, Alex, and I'll catch you up on him later. But he called this out. He's like, you know, it's interesting. Like, he believes the bet we're making on spatial is the right bet, but it's also an expensive one. And just like how we consider the cost of spatial and what we introduce, you know, like how much we introduce within this environment that makes it accessible for people. And then we went into the conversation of native versus the web, and really, like, you know, what you get with either of those. So just sidebar, wanted to say that we'll have larger discussions on it later.
Yeah, I would love to be a part of that. That's an interesting conversation.
Yeah.
And with like Apple's recent push, you know, to spatial computing, that also might be an interesting bet to play, because if you have Canvas, all the related things, you know, how easy is to translate that into an actual environment and use, you know, let's say Apple, how they call it, Apple Vision Pro, right? In order to display, in order to display and navigate, you know, pretty much the same canvas.
Well, and especially when you add deformability, where now I'm zooming, but not everything is changing size at the same rate, and we're able to. There's a lot of things that you can do with that, and if you do that well, it could create a really magical experience where, I mean, you break out. It would be the next evolution where it's not spatial canvas. It's I don't know what you would call it, but it would be another thing.
Yep.
Yeah. Cool, guys. Just a time check. We're at 10 minutes.
Well, so that's everything that I wanted to present and talk about. So I'm happy to answer any more questions. Whatever y'all think is appropriate.